Hello, this video is going to be covering concepts from the Unbalanced Force Particle Model unit. The first thing to notice here is I have a list of skills that you need to have going into this exam. Make sure you review that list of skills and that you're strong in all these areas and that you know what it all means. Because when I make the exam, these are the sorts of things that I'm looking at. I want to test these different skills. One thing to point out here is I say that I'm going to give you some different force equations, but that you're going to have to know how to apply those equations. You're going to have to know what the different variables mean and what units need to be plugged in and things like that. And so while I'll give you the equations for some of the forces, you yourself have to know how to use those equations and what all the different variables mean. Section A on this is about concepts and understandings, and so I ask you a series of concept questions. I've got the answers in here already, but I'll sort of discuss some of the rationale that we have. Number one says, what is true about the direction of acceleration for an object compared to the direction of its velocity if the object is speeding up? If objects are speeding up, velocity and acceleration are pointing the same direction. If they're slowing down, velocity and acceleration are pointing opposite directions. That's just an old concept from the last unit that is important to remember still in this unit. Problem number two says, an object is accelerated by an external unbalanced force. If the object's mass is doubled, but the external unbalanced force remains the same, what happens to the object's acceleration? And so this problem is thinking about the relationship between force, mass, and acceleration. When you consider problems like this, I encourage you to think of an analogy I made about a shopping cart, all right, where we have a shopping cart that you can fill with groceries, which would be adding more mass, or you can take groceries out, which would be removing mass. You could push harder on it, which would be adding a larger force, or you could be pushing less on it. And then the acceleration has to do with how fast the shopping cart is speeding up or slowing down. And so this one says an object is accelerated by an external unbalanced force. If the object's mass is doubled, but the external unbalanced force remains the same, what happens to its acceleration? So what we're doing here is we're doubling something's mass. And there's a force on it, but we're keeping the force the same as it was originally. So if you have double the mass, but you're pushing on it with the same force, the acceleration gets cut in half. Make sure that you could think about other different alternatives of this. For instance, if I said, let's say you wanted to maintain the same acceleration and you doubled the mass, what would you have to do to the force? Well, if you wanted to maintain the same acceleration and you doubled the mass, you would have to double the force as well to maintain that same acceleration. Things like that. Problem number three is just making sure that you have the connection between these different models. Constant velocity goes with balanced forces. Constant acceleration goes with unbalanced forces. Question number four hits another important point of this unit. If we know the direction of the unbalanced force, we also know the direction that that object is accelerating in. All right. We know that it's going to have balanced forces in the direction perpendicular to that acceleration, which we take into account on a lot of different problems. And then we also know that the rightward forces would be larger than the leftward forces. On to page 2 here. We have a few questions about this graph. The first thing to notice, anytime you're looking at a graph, you need to figure out what sort of graph it is. This is a velocity versus time graph. Question number 5 asks, during which periods of the graph are the forces unbalanced and how do you know? I've got the answer here. It's a velocity versus time graph. So the forces are unbalanced whenever it's accelerating. You can tell that it's accelerating during A and C because those are both sloped periods of the graph. And if something has a slope, that means it's accelerating for the velocity versus time graph. Which means that the forces are unbalanced. Number 6, it says which periods have the largest unbalanced force? All right, what period has the largest unbalanced force and is it in the positive or negative direction? C here you can see has the greatest slope. All right, so it is the largest unbalanced force. And it's going in the positive direction because that slope is upward. Number 7, what's true about the direction of the acceleration and the velocity vectors for the object during period A? So during A, it's got a positive velocity because actually during all of these periods it has a positive velocity. If your line is above the t-axis, meaning that it's in the positive part of the velocity graph, it's going to be positive. In order for velocity to be negative, it's got to be somewhere down in this region of the graph, which it doesn't even exist on this one here. So all of these velocities are positive. And then we know that the acceleration is negative because it's got a negative slope. Also, it's slowing down. So getting on to section B, where we have some problems here. The first one is about a 2,000 kilogram boat, and I give you the initial velocity there. It's accelerating across the lake. I said there's a forward applied force of 6,500 newtons coming from the motor, and there's a water resistance force which is also applied, which is 2,500 newtons. It impedes its movement. And so hopefully you have everything you need there to kind of think about the different forces that would act here. It's going to be accelerating horizontally because it's a boat, so it's going to be accelerating off here to the right, I'm going to assume, because we just normally say that the right is the forward direction. And so what we've got here then is we've got our object. There's a gravitational force on it. Fg is 2,000 kilograms, so that's going to be a 20,000 Newton force. All right. Additionally, we've got, in this case, the thing that's keeping it up is the water, so it's a buoyant force. And that also equals 20,000 newtons because it's not accelerating in the vertical direction. It's accelerating to the left and to the right. So we know that these are the same. The other two forces, we have some sort of applied force pushing the boat forward from the motor. That's Fa, which equals 6,500 newtons. And then there's another resistance force coming from the water, and that is in the negative direction, and it is 2,500 newtons. So Fa equals 2,500. All right, and so that is our FBD. You can see here that it is unbalanced going left and right. It is unbalanced by 4,000 newtons. So Fu equals 4,000 newtons. We want to find the acceleration. We know Fu equals ma. All right, this actually can be rearranged to say A equals Fu over m, which oftentimes is useful. And so we know that A equals 4,000 over the mass, which is 2,000. All right, so 4,000 over 2,000 is 2, and its acceleration, so it's meters per second per second. And the direction of this is to the right. Or actually, in this case, I'm going to say forward because forward was what was used in the problem. So on to part C, we need to draw velocity versus time graph and figure out how far it's going to travel in 20 seconds. Remember here from the top, though, that it has an initial velocity of 5 meters per second. Many people, when they're doing this type of problem, they forget to look back at the original set of conditions, but that's important in solving this next part. We make a velocity versus time graph. It starts with an initial velocity of 5. All right. So what we get here is we get one of these ones where we have a shape where it's a rectangle and a triangle. The next thing I'm going to do is figure out what the change in velocity is. All right, well, I guess I should say we know that this is 20 seconds here because it's given us the time. The next thing I can do is calculate this change in velocity, which is from here to here. I know that change in velocity equals acceleration times time. That's just a rearrangement of the slope equation for the velocity versus time graph, which in this case equals 2 times 20, all right, which is 40 meters per second for your change in velocity. And so what we have here then is we have two shapes. All right, we have a rectangle and we have a triangle. All right, we want to get the area for both of them. So I know that for the triangle, 1/2 times the base, which is 20, times the height, which is 40. Okay, that's the area there, and I want to add that to the area of the triangle, the rectangle. So the rectangle has side lengths of 5 and 20. All right, and then you add those together. You should come up with 400 plus 100, which is 500 meters. So you've seen here a problem where we have an unbalanced force, we make an FBD, and then we go to create the velocity versus time graph at the end. Problem number 2 also involves a velocity versus time graph, and an FBD, but it's going to actually flip-flop the order. So on this one, I give you some information about its motion, all right, which we're going to use first, and then we're going to use the FBD. Although I actually always make the FBD kind of at the beginning, but then I come back to it later if I need to. So this is a man standing in an elevator. By the way, when you read this problem, a lot of people think that this 2,000 kilogram elevator is an important piece of information, but it's actually not. All we care is that it's an elevator and it's accelerating downward. And then, because what we're really talking about here is the 100 kilogram man on the elevator, and I tell you to find his apparent weight, and so we're really concerned about him. So the gravitational force for the man is 1,000 newtons. It's accelerating downward, so you know that the normal force is going to be less than the gravitational force, because if it's accelerating downward, that means the larger force is downward. Here's the problem. We don't know what that normal force is until we figure out how unbalanced these forces are. In order to figure out how unbalanced the forces are, we need the acceleration. To figure out the acceleration, we're going to make a velocity versus time graph. So it starts from rest and it's accelerating downward. I could see reasons to do this either way, but since it's going downward, I'm going to kind of consider that to be negative. Some things that we know here. It says it moves 60 meters, so the area of this is 60, and it says it does that in 12 seconds. What we can do here then is we can figure out what the change in velocity is here, because we know that 1/2 times the base, 12 times the height, change in velocity, equals the area, which is 60. We rearrange that, and you should find that change in velocity equals 10. All right, so this side equals 10. Then to figure out the acceleration, we know that acceleration is the change in velocity over the change in time, which is the slope of this velocity versus time graph. All right, change in velocity is 10. The change in time is 12. 10 over 12 equals 0.833 meters per second for our acceleration. All right, so that's our acceleration. Now that we've got acceleration, we can do Fu equals ma, which equals, in this case, 100 times 0.833. You calculate that, and you should get 83.3. All right, so we know that these forces are unbalanced by 83.3. We also know that the gravity is 1,000 and that the downward force is larger than the upward force. So logically speaking, what this tells us is that the normal force is 83.3 newtons less than the gravitational force. If that's the case, then we just need to take 1,000 minus 83.3, and what we get is that the upward force is 916.7 newtons. All right. I asked you for the apparent weight. I don't think I talked about this before, but the apparent weight is the normal force between a person and whatever they're standing on. And so the normal force is the apparent weight. All right. So that is the answer that we're looking for. Weight is a force. It's the gravitational force. Apparent weight is a normal force. It's in newtons. Many people think that weight should be in kilograms, but that's just a misconception that comes from the fact that in Europe, when you ask people their weight, they give it in kilograms. But in science, weight is measured as a force. It's measured in newtons. All right. Mass is measured in kilograms. And so when I ask for the apparent weight, I'm asking for the normal force between a person and whatever object they're standing on, and it's measured in newtons. So 916.7 newtons. Problem number 3 here is a multi-bodied problem. So the key here is that there are two different objects that we're interested in, and I ask you for a force between them. That kind of gives you a clue that I might be talking about a multi-bodied problem. And so what we're going to do here is try and create FBDs for both of them and fill out what information we can. So I'm going to start off with the trailer. Which is in the back. I started out with that one because it's going to be the less complicated of the two. If you don't know which one's going to be less complicated, I would just kind of start to draw both and then think about it later. So trailer has a gravitational force on it, Fg. It has a normal force on it, Fn. All right, and then it's got a force pulling it forward from the truck, which I said is a normal force applied from the hitch. All right, so the gravitational force, we can tell because it's a 600 kilogram trailer, is going to be 6,000 newtons. We know the normal force is actually going to be 6,000 newtons as well because this trailer is going to be accelerating to the right. It's not going to be accelerating up and down. The thing we don't know is this normal force here, and this normal force is between the trailer and the truck. All right. The way we figured this out, though, is because we know the trailer is accelerating, and if we also know its acceleration, we know the mass of the trailer, so we can do Fu equals ma. For the trailer, and we get that it is 600 times 4, which is 2,400 newtons, unbalanced. Now, if we look back at this trailer diagram, the only unbalanced force is that normal force that's going off to the right. So we know that takes on the entire 2,400 newtons. The next thing I'm going to do is make an FBD for the truck. So on this truck, we have actually 4 forces acting here. We have Fg. We have a normal force up. I said there's a forward friction force on it. This is the one that pushes the truck forward, or it's between the tires and the road, is the friction force that pushes the vehicle forward. All right, and then I also have a normal force pulling back on the truck that's coming from the trailer. So the trailer is pulling the truck backward. And I kind of know that's going to be smaller here than the frictional force. All right, and so this is F normal on the truck by the trailer. And one thing here, if you remember Newton's third law, we know that the normal force on the truck by the trailer is equal in magnitude and opposite in direction than the normal force on the trailer by the truck. So this is also 2,400 newtons. Gravity for the truck is 12,000. Normal force going up has to be balanced because it's not accelerating in the vertical direction, so that's also 12,000. And then the friction force, to figure that out, we have to do another Fu equals ma, this time for the truck. So we know Fu equals ma for the truck as well, which for the truck equals 1,200 times 4, which gives us 4,800 newtons. Okay, this tells us that the forces to the left and the forces to the right are unbalanced by 4,800. 2,400 to the left, that means we have 7,200 to the right to balance out. All right, so now we have in this problem, we found that the friction force on the truck is 7,200, and then we know that the normal force between the truck and the trailer is 2,400 newtons. Problem number 5. This is a problem that involves some of the force equations. There are 3 of them that you're responsible for. There's the buoyant force equation, there's the friction force equation, and then there's the spring force equation. The 2 that come up in this one are the spring force equation, which is FSP equals Kx, and also the friction equation, FFR equals mu times Fn. We're going to use both of those. The K in the spring equation is the spring constant. The X is the distance that the spring is stretched. The mu in the friction force is called the friction coefficient. All right, so now we think about this box. It's being pushed by a spring off to the right, presumably here, and there's a friction force resisting its motion. So we have on this object Fg going down, Fn going up. We have a spring force, Fsp, going to the right. And then we have a friction force, Ffr, going to the left. Some things we know here is 5 kilograms. So the gravitational force is 50 newtons. It's not accelerating the vertical direction, so we know that the normal force is also 50. From here, we don't know what the spring force is or the frictional force is, but if you look at the force equations, we have enough information to calculate the friction force because we know Fr equals mu times Fn, which in this case is 0.6 times the normal force, which is 50. Right? And that equals 30 newtons. The next thing we can take advantage of is we know the acceleration of this object, so we can figure out how unbalanced the forces are by using Fu equals ma. That's 5 times 3, which gives us 15 newtons. So we know that the forces are unbalanced by 15 newtons. Furthermore, we know it's accelerating to the right, so the rightward force needs to be 15 newtons more than the leftward force, which means that the spring force is 45 newtons. We are pretty close here then to the end of the problem. The last thing that we're going to do is look at the spring force, which we know equals kx. All right, so then 45 newtons equals k. It was given in the problem. It's the spring constant. It's 3,000 x. Divide both sides by 3,000, and we get x equals 0.015 meters, or you could write it in centimeters. It would be 1.5 centimeters. Problem number 5 here. This one is an angled force problem, and so there are 2 ways that these could happen. I'm either going to give you one of the angles at a force, and then you're going to break it into components. All right, and then there will probably be an acceleration or an unbalanced force that is on the horizontal or the vertical axis. Or in this case, what I'm going to do is I give you a bunch of forces that are on the horizontal and vertical axes, but the unbalanced force ends up being at an angle. All right, so here's what happens on this one. It's an airplane. Airplanes still have gravitational forces, so Fg equals, in this case, it's a 50,000 kilogram airplane, so it's going to have 500,000 newtons of force downward. I tell you that there's an upward lift force, which we're going to call an applied force, and that equals 600,000 newtons. All right, and then other than that, we have a forward applied force. This is the propulsion force coming from the engine. It's pushing the object forward. That has a magnitude of 80,000 newtons. So then what we do is we compare these in size. Up and down, it's unbalanced. Left and right, it's unbalanced. Overall, the unbalanced force is going to be going up and to the right. So I draw in here my unbalanced force, right? And I know that it's got components. It's unbalanced left and right by 80,000. And it's unbalanced up and down by 100,000. Then what I can do is I can use some trigonometry here, say the Pythagorean theorem, and figure out that the magnitude of my unbalanced force here is 128,000 newtons. And then to figure out what the angle of inclination here is, this theta, what I can do is I can say that theta equals the inverse tangent. Anytime we want an angle, we're going to have to use an inverse trig function. So inverse tangent, I think, makes sense in this case because the 2 numbers that we knew the earliest were those sides of that triangle. So 100,000 over 80,000. And what we get here is 51.3 degrees. Okay, and so as a final answer, FU equals 128,000 newtons at 51.3 degrees above the horizontal, or I'll call it ATH. This last problem here, you can see that we've got an object. It's on an inclined plane or on a hill. That means that we're going to follow the strategy for inclined planes or for hills. Generally speaking, we start these by making an FBD. There's a gravitational force downward. And actually, I try and make these really, really big, just so that I have lots of room for the angles that go in there and any numbers that need to be written. So we're going to have a gravitational force downward. All right, additionally, on this one, there's a normal force. There's actually, on these inclined plane problems, you've got an object sitting on a hill, so there's always going to be a normal force. That normal force is going to be going up and to the left, and actually I kind of want to slope it even a little bit more, because if I think about the direction that this is going to go in comparison to that plane, I think that this looks a little bit better. All right, then next, the object is sliding down, but I say that there's a friction force on the box. I kind of give you that as a hint by the question, and so we know that that friction force is going to be going this direction, up the hill, because if the box is sliding down the hill, the friction force goes up the hill. And then on every one of these inclined plane problems, what we do is we break down gravity into components. All right, there's a right angle here that gives us two axes. And so what I'm going to do is I'm just going to extend this line. All right, and then I want it to hit at a right angle and get back to my gravitational force. And so I think if I do that, it looks pretty good. I'm going to erase this extra. So we've got a little right angle that gets in here. And so now I've broken my gravity force down into components that are parallel with the friction force and the normal force, so that I can have them sort of cancel out with each other. So I've got kind of a force that's going this way, a component that's going down the hill, and a component here that's going perpendicular to the hill and still kind of down. And those are my two components of gravity. It's a 2.5 kilogram box, so I know that it's 25 newtons for the gravitational force. The next thing I need to do is figure out the angles involved in this problem. What we've got, if I make this little snowflake thing that I have taught you, is I have to figure out where this 20-degree angle falls in here. I look at this here. All right, we got a horizontal going this way, and so I look for this wedge on my snowflake. It's right here. So this is 20 degrees. Then I have to fill in the rest with complements and things like this. So this is 70 degrees, and then it just goes back and forth. 20, 70, 20, 70, 20, 70, 20, 70. All right? So I've got that. Now I'm looking for the one that goes along with my gravitational force. My gravitational force is straight down, and then I've got something going off to the right, and so, or going off to the left. So we've got kind of down for my gravitational force, and then this angle off here. And so you can see there that that's 70 is what we're looking at here. So this is 70 degrees. Now that we know that, that allows us to do some trigonometry on these triangles. We know that the sine of 70 is going to give us the side that is opposite there, which I'll call x. All right, and we know that the cosine of 70 is going to give us the adjacent side there, which I'll call a. All right, and so you go through and you do that, and hopefully you should find 23.5 for this side. And for the other side, you should find 8.55. All right, so those are the components of gravity that we're going to be using. Now you have to think in this problem, what direction or what axis is it accelerating along and what axis is it not accelerating along? This box is going to be going down the hill. It's going to be accelerating down the hill, and so it's going to be accelerating along this axis. The axis that it will not be accelerating on is the axis that's perpendicular to that, which looks like this. It's not going to be accelerating on that axis, the red one, because then it would leave the hill, it would lose contact with the hill. And so what this tells us is that it's balanced in that direction with that red axis that's perpendicular. If you find the two forces on the FBD that are going perpendicular to the hill, that includes the normal force here and then that component of gravity that is perpendicular to the hill. That means that the normal force has to be 23.5 newtons in this problem, which actually was extra information. It didn't ask us to find that, but just good to think about because that normal force needs to cancel out directly with that component of gravity that is perpendicular to the hill. Now, in terms of the direction that it's going to be accelerating in the direction of down the hill. We have one step further to do because friction isn't going to equal 8.55. If that was the case, then it'd be constant velocity because the forces would be balanced. The forces are unbalanced. We have to figure out how much the forces are unbalanced by. How we can do that is we can use Fu equals ma. In this case, mass equals 2.5, acceleration equals 2, so Fu equals 5 newtons. So that means that they are unbalanced by 5 newtons. We've got the friction force going up the hill, and we've got that component of gravity going down the hill that's 8.55 newtons. All right. The down the hill component is going to be winning out because this box is going to be accelerating down the hill. So that 8.55 newton force down the hill needs to be 5 newtons more than the friction force. If it's 5 newtons more than the friction force, then that means the friction force is 3.55 newtons up the hill. Then we have an unbalanced force of 5 newtons. There are 5 newtons more going down the hill than is going up the hill. All right, so that is our friction force, and that is the answer to this problem. So I know that these problems are all pretty tricky. There's a lot of different types. My suggestion is that you look back through this packet, figure out what types of problems you're confused about, and do some extra practice with those. If you have any questions, generally speaking, make sure that you stop in and ask. Otherwise, hopefully you'll prepare and put the time in to learn all these different types of problems and then do pretty well on the exam.